Hi, I'm Conor Hodden, and this is the fourth lecture in the information theory section of our unit, Information Processing and the Brain. And today I'm going to be talking about mutual information, probably the most fundamental object in information theory, more fundamental in some respects even than the Shannon's entropy. To motivate the mutual information, I'm going to go back to this formula, which we saw at the end of the last lecture. It's the chain rule, so-called, for entropies. It says that the entropy of the joint distribution, h of x comma y, the joint entropy, is equal to the entropy of the of x plus the conditional entropy of y given x. In other words, the amount of information contained in x and y together is the amount of information contained in x plus the amount of information remaining in y if you know x. Makes sense. I'll try and illustrate this with a little picture. So this blue bar here is supposed to represent the information in x. It's how much we'll learn if we know the value of the experiment x, if we draw from x, or put another way, it's the uncertainty in x, a measure of that uncertainty. Similarly, this yellow bar represents the entropy of y. But if we look at them both together, they overlap. So h of x comma y is less than h of x plus h of y, because the information in, well, if x and y, assuming x and y aren't independent, the information in x it overlaps with the information in y. And indeed, that's exactly what the chain rule is telling us, that the information left in y, when you know x, is smaller than h of y by this overlap amount, as it were. So h of x comma y on top, the total information in the joint distribution, is equal to the information in the x distribution plus the information remaining in the y distribution if you know about x. And we can think of that as the consequence of there being some overlapping information. That's the information that's in x, which, if you know it, reduces the amount of information in y. And of course, we've written everything in a very sort of x beats y version, because it's what we're looking at is h of y given x, but we can do it the other way around. It's the same. The chain rule has well, h of x comma y is symmetric in x and y, and so there's two versions of the chain rule, an x1 and a y1, as it were. But the interesting thing is this little green portion in the middle. This is the information that x tells us about y, or that y tells us about x. It's the bit that you have to remove to get the total information of x and y together. And so that little green box is the shared information. It's the information that you lose from y if you know x. It's the information that you lose from x if you know y. It's the information that the two random variables share. So that's clearly an important thing that should have a name, and it does. That name is the mutual information. So here's the picture. The total information in x and y together is equal to the information in left in x if you know y, the information left in y if you know x, plus the information that they share. That's not, so that tells you, and it is true, that h of x comma y, the joint entropy, is equal to the sum of the two conditional entropies and the mutual information. That's the normal way to define the mutual information. Usually we do it this way. So we know that the joint entropy, h of x comma y, is less than the sum of the two entropies, h of x and h of y. So h of x comma y is less than h of x plus h of y, because h of x and h of y have an overlap. And so this formula tells us that the mutual information is equal to h of x plus h of y minus h of x comma y, because h of x plus h of y includes the overlap. And so that is a common way of defining the mutual information, although it's sometimes defined directly from the probabilities, as we'll see in a second. That's not the only formula we commonly use for the mutual information. Here's another one, which kind of goes back to the description we just gave. The information in x is made up of two bits: the information that's remaining in x if you know y, plus the information x shares with y. So from the picture, we imagine that I of x comma y is equal to h of x minus h of x given y. So it's equal to all the information in x, and kind of the information in x that's its own business. The information that remains in x, or the randomness that remains in x, if you know y. I did that with a picture, but you can quickly check that it also kind of makes sense by taking the first formula I wrote down, the formula for the mutual information I of x comma y is equal to h of x plus h of y minus h of x comma y, and then substituting from the chain rule. So h of x comma y is equal to h of y plus h of x given y. Substitute the second line into the first one, cancel the things that cancel, and you get the final line. And of course, once again, that's kind of a x-centric formula, but I of x comma y is symmetric in x and y. You can tell that from the top formula and the fact that h of x comma y is symmetric in x and y, and so you could do it the other way around as well. So I of x comma y is also equal to h of y minus h of y given x. Good. So that's the motivation. These are the formulas we've come up with. They are all related by the chain rule. The first one was the one I'm sort of announcing as the definition. The second two we just derived. And the final one was the one that we showed in the picture on the first, right back here. That's the fourth of those formula. Again, they're all related by using the chain rule. I mentioned earlier that you could also write a formula for the mutual information directly in terms of the probabilities. You get that by taking the first formula, for example, I of x comma y is equal to h of x plus h of y minus h of x comma y, and just substituting in the formula for h of x and the formula for h of y and the formula for h of x comma y in terms of probabilities. And this is what you end up with. You should check that yourself, or a slightly easier task is to start off with this formula and see that it reduces to the first of those formula there, h of x plus h of y minus h of x comma y. Basically, you get the log, and you expand it out in the usual way. The log of p of x comma y over p of x, p of y is equal to the log of p of x comma y minus the log of p of x minus the log of p of y. And then you end up with some of the terms. You can sum out either the x or the y to reduce the joint probability in the factor multiplying the log to a marginal probability. So that's the formula, the direct formula, as it were, for the mutual information. You can see it says that the mutual information is equal to the expected value of the log of the ratio between the joint probability and the multiple of the marginal probability. So, the point is that the joint probability is different from p of x comma y is different from p of x multiplied by p of y, precisely because because x and y are not independent. And we'll return to that point very shortly. First of all, let's do a quick example. This is returning back to the example we had before. In the last day, with the simple joint distribution, the last day I worked out these entropies. We saw that the joint entropy was 3 over 2. The entropy of x was 0.81-ish, because it was the log of something. And the entropy of y was equal to 1, which you can easily see, because if you marginalize y, it's y0 has a chance of half and y1 has a chance of half. So it says maximum entropy for a two-element set. And so if you add hx and hy and take away h of x comma y, you get 0.31. And that works because h of x comma y is necessarily smaller than h of x plus h of y. So the mutual information is going to be positive, a fact I'm going to assert in just a minute. On that note, I already commented on the fact that the mutual information is the expected value of the log of the ratio of the joint distribution and the multiple of the two marginal distributions. If x and y are independent, then the joint distribution is just the multiple of the two marginal distributions, in which case that thing inside the log will be 1, and the log of 1 is 0. And so in the case where x and y are independent, the mutual information is 0. In fact, you can make the statement stronger. Again, we're not going to prove that, but it's not that difficult to prove that the mutual information between x and y is always positive. That's kind of what you want. The mutual information between x and y is the information they share. It's how much information one tells you about the other. That should be positive, and indeed it is. And beyond that, it's in fact only equal to 0 if x and y are independent. And that shows you what kind of an important object this is. It is a quantity you can calculate on two random variables that's only 0 if the two random variables are independent. So it's clearly a good measure of the relationship or the degree of relationship between the random variables. Just before I say a little bit more about that, to note in passing that because h of x comma y is equal to h of x minus h of x given y, that was one of the definitions, if you remember. That tells you that h of x, well, if the mutual information between x and y is always positive, that tells you that the entropy of x is always greater than the entropy of x conditioned on y. That the entropy of x on its own is bigger than the entropy of x when you know something about it, i.e. you know the value of y, a possibly dependent, not independent variable. We made that claim before. I didn't prove it then. I'm now just pointing out its equivalent or can be derived from another fact that I'm not going to derive. But at least it all holds together, as it were. On the point of independence, you should just note in passing that the one way that we often check whether a variable is dependent on each other is to work out their correlation. So this is the correlation function, or the correlation rather. It's the expected value of x minus its mean multiplied by y minus its mean divided by the standard deviations. And obviously, this kind of works by saying if whenever x gets big, y gets big, and when x is small, y is small, and if when x is a big negative number, y is a big negative number, where all those statements are after taking out the mean, then the correlation is going to be non-zero. So if x and y have some sort of linear or linear-like relationship, or one increases monotonically, maybe noisily, but tends to increase monotonically as the other does. If there's any of those relationships, there's going to be a non-zero correlation. And so very often correlations are taken as a way to see if two random variables are not independent. And indeed, if the correlation is non-zero, the two random variables are not independent. But we should note for a start that this correlation, as we mentioned at the very start, as with the mean, as we described at the very start, the correlation only works if x and y take their values in a vector space. We have to be able to meaningfully multiply something more than a vector space. We have to be able to meaningfully field properly. We have to be able to meaningfully multiply the outcome of the experiment x by the outcome of the experiment y. The xi's and the yj's have to be objects that you can multiply by each other. So this correlation is only defined in the case of, particularly in the case of random variables that take values that have nice algebraic properties. So that's the first thing. So it's clearly a less fundamental object than the mutual information, which is defined on all joint distributions, because it only depends on the existence on the space of outcomes of the probability distributions. The correlation, secondly, only spots certain sorts of relationships. So here's an extreme example. So if we look at this this probability table, so x here can take the values -1, 0, or 1, and then y, the value of y will always be the square of the value of x. So if x is minus a half, y will be 1. If x is 0, y will be 0. If x is 1, y will be 1 as well. So this table here is a table for two random variables, x and y, that are completely dependent. If you know x, you know y. If you know where you are horizontally, you know where you are vertically. And then I've also taken it so that the probability of getting x equals -1 is a quarter. The probability of getting x equals 1 is a quarter. The probability of getting x equals 0 is a half. So that probability table there is a probability for two variables that are not independent. In fact, they are, highly dependent. But the correlation function, if you calculate it, I haven't written it out here, it's in the notes, the correlation function is 0. Conversely, as you would hope, or as I've asserted, the mutual information between those random variables is 1. So you can see that this is only the sort of the start of the story. The mutual information is the correct object for describing the degree of relatedness of two variables. And one of the things it should be able to do, and in fact does, is it should be able to indicate whether variables are independent or not. And here's an example where the correlation, which is very commonly used to measure the relationship between variables, says that two variables are dependent because their relationship are independent. Well, it says the correlation is 0, and that's correct. I mean, the correlation is looking for only this very particular type of relationship, lacking in this probability distribution. But that might mislead you into thinking that the two variables were independent, when in fact they're not. Of course, the big advantage of the correlation function is that it's very easy to calculate, or can be quite robustly estimated. The correlation function is just the expected value of basically x multiplied by y. And so if you draw values xi and yj, you can just multiply them together, add them, divide by the number of pairs of values you've chosen, and that gives you a good estimator of the correlation function. Estimating the mutual information is more complicated because you have to estimate the actual value of the probability distribution itself, which tends to take more data. You have logs there as well. The log of small numbers gives you minus infinity. So if there's pairs that rarely occur and you draw lots of data from your distribution, maybe some of the pairs won't occur, and then you'll end up with zeros and hence infinities in your estimator. So the correlation function does have the advantage that it's easier to estimate, but for our more theoretical work, where you're trying to understand, at the end you want something that you can estimate easily, but on the way you want to do some mathematics with the probabilities, with the relationships between the variables, in which case the mutual information will often be the quantity you're after. So again, in summary, I've motivated the mutual information. We've seen some identities relating it to various entropies, joint entropies, marginal conditional entropies, etc., and a formula relating it directly to the probability distribution. But the main thing is the mutual information is a measure of the information shared by two variables, and in that way, it's a measure of the relationship between two random variables. Thank you.